Good evening to everyone. This is Madhu from IEEE PS5P Technical Activities Coordinator. Welcome all to the participants to this science gathering in this virtual webinar to hear on coordinated planning of electric vehicle charging process and renewable and power grids. Now, I would like to invite Mr. Subir Muzamdar to introduce the speaker. Go ahead, Subir.
Sure. I'll take this opportunity to introduce Dr. Bo Yang. Bo Yang received the BSc degree in automation from Jilin University, Changchun, China, in 2013. The MSc and PhD degree in electrical engineering from George Washington University, Washington, D.C., USA, in 2015 and 2020, respectively. He is currently a power electronics engineer with Amazon Web Services. His research interests include electric vehicles, power system optimization and control, and smart grid reliability. With that, I would cordially like to request Dr. Boyang to present us with his talk titled "Coordinated Planning of Electric Vehicles Charging Infrastructure and Renewables in Power Grid." After you, Dr. Boyang. Thank you.
Yeah, thank you. Hello, everyone. I'm Bo and thank you for attending this webinar. This is the agenda. First, I will introduce the background and motivation of the research, overview the literature, and discuss the research gap. Then I will introduce the new control and energy management scheme. Next, system identification and electric vehicle charging infrastructure planning for power grids with electric vehicles and distributed energy resources are achieved. Some case studies for the proposed approach are provided. Finally, I will highlight the contributions of this work. A power grid transformation is needed to achieve the net zero carbon emissions in 2050. The International Renewable Energy Agency has published a roadmap to achieve this goal. So we can see in this figure that by 2050, there will be 70% of the emission reductions, where renewable energy and electrification together deliver 75% of the emission reductions. It is forecasted that around 86% of the electricity comes from renewable resources, and about 60% of the total power generation will be accounted by variable renewable energies, such as solar and wind. For the vehicle use, by 2050, around 70% of all vehicles would be powered by electricity. It requires an increasing smart, digitalized, and flexible power system. This research tries to focus on how to use electric vehicle load to adapt to variable renewable energy power and how to deploy variable renewable energies and electric vehicles at a large scale quickly and cost effectively. This section is problem statement and literature survey. To the lower level control scheme of the electric vehicle supply equipment, there are different charging mechanisms. Conductive charging. The battery is connected by a cable and plugged in directly into the electric vehicle supply equipment. Based on the power level, smart charging typically uses 5 to 20 kilowatt. Fast charging usually is between 50 to 60 kilowatt, and super fast charging from 150 to 350 kilowatt. This is inductive charging. The electricity is transferred through an air gap from one magnetic coil in the charger to a second magnetic coil fitted into the car. Battery swapping. The electric vehicle battery will be swapped with fresh ones in a battery swapping station. Inductive charging and conductive charging share similar power levels. To the higher level energy management scheme of the smart charging stations, the current research typically uses decentralized scheduling and has strong assumptions on electric vehicle customer behaviors. It will cause some oscillations of the charging loads with increasing electric vehicle penetrations. In this presentation, we introduce new smart charging station architecture that considers interconnection and interoperability with modern electric power system interfaces. Specifically, we consider IEEE standard 1547 in the smart charging stations. We introduce a two-stage energy management system architecture to improve power system performance. We are a nearly optimal solution, and at the same time accounts for variable renewable energy forecast uncertainties and the stochastic randomness of the electric vehicle customer behaviors. Regarding to the electric vehicle charging infrastructure expansion planning, the majority of the recent literature either focuses on the deployment of fast charging stations in urban areas, or use simplified demand-side models without considering smart charging and coordinated planning of electric vehicles and distributed energy resources. The proposed schemes use direct load control and can consider a combination of charging methods. So we can quantify the nearly optimal electric vehicle charging load ratio in different regions under different electric vehicle and renewable penetrations. When the smart charging is the main charging method and fast charging, super fast charging, and battery swapping alternatives are the complementary charging methods. We also estimate the capacity of different EV charging stations, including smart charging station, fast charging station, super fast charging stations, and battery swapping stations to support potential large-scale electric vehicle charging demand and high variable renewable energy penetration. We introduced the proposed lower level control and higher level energy management schemes in this section. First, we introduce the situation that the electric vehicle load works as a deferrable load. The top figure shows a typical advanced metering infrastructure. The smart meter connected to the electric vehicle will communicate bidirectional signals with access point. And the access point can also communicate with the utility meter data management system through the backhaul system. The utility in Washington, D.C. area has built such system in 2016. So the utility can turn on and off the smart meters remotely. A new advanced metering infrastructure architecture is proposed to support the electric vehicle dispatch communication, as shown in this figure. Computation loops are added to the feeder level. With the online computation loop, the data will be classified and processed, and only aggregated information needed will be uploaded to the utility. So we can shrink the volume of the data to be uploaded to the utility meter data management system platform and achieve a fast and efficient energy management. This case is case that the electrical vehicle load works as a distributed energy resource. So the smart charging station is connected with the main grid using a step-down transformer. This is a AC-DC converter and this is DC-DC converter. The physical system is in black color and the communication system is in blue color. The control center with the site monitor will monitor and control the whole smart charging station. So it is a three-phase large-scale smart charging station with tens to hundreds of electric vehicles. The Smart Energy Plaza at Argonne National Laboratory uses a similar architecture. We propose additional operation states and control modes so that the smart charging station will comply with IEEE standard 1547. This figure shows the smart charging station operation states and a priority diagram as a DER. The smart charging station will disconnect from grid if it receives a disabled signal. During the abnormal condition, it will first try to ride through the disturbance and then trip if it satisfies the tripping requirements. This figure shows a recommended ride-through priority and mode selection diagram. We have two active power mode and four reactive power mode. Since smart charging is used and the increase in peak loads is avoided most of the time, it will mitigate the voltage drops in the distribution system. The voltage drop can be also compensated by the smart charging station and the regulating transformer. If smart charging station works as a DER and voltage reactive power mode is used. So in this study, we only use the DC optimal power flow in the planning issue, and the reactive power is not considered. This slide shows the EV load aggregation based on direct load control. In the smart charging station, the cumulative energy LC that is expected to be allocated to the plug-in electric vehicles at next time step is equal to the LC at current step plus the total power allocated at this time step. The total power allocated will be distributed to each aggregator proportionally. And the aggregator will use an algorithm to prioritize EV charging priority. Here we use a sorting-based algorithm to prioritize EV charging. Three signals will be connected from electric vehicles to the aggregators. The estimated departure time, the estimated minimum energy upon the electric vehicle departure, and the current state of charge. We collect the same information as the Smart Energy Plaza at Argonne National Laboratory. Then the upper and lower charging constraints can be uploaded to the independent system operator, where the transformer loading can also be considered in the upper charging constraints. So these charging constraints are the time vary constraints. In the battery swapping station aggregation model, we have fixed capacity for the battery swapping station. So we can use stationary battery storage model, except that we have the addictive battery swapping load. The charging sessions in the battery swapping station can be regarded as a queuing model. Regarding to the fast charging aggregated load, the LC is an elastic load which can be predicted directly using load forecasting algorithm. And the charging sessions in the fast charging station and the super fast charging station can also be formulated as a queuing model. The proposed simulation framework is shown in this figure. The first stage is a 24-hour ahead dispatch. It is run in the control center of the independent system operator. The second stage includes 3-hour ahead dispatch, and the communication between the independent system operator and the charging stations. The communication signal can be either sent through advanced metering infrastructure or the distributed energy resources communication networks. This figure shows the individual EV activities of smart charging EV customers. If an electric vehicle is parked and it subscribes to the battery swapping service, it will use smart charging then its state and swap its battery if the SOC of the battery is lower than the SOC threshold then the driving. If an electric vehicle is parked and it does not subscribe to the battery swapping service, then it will use fast charging or super fast charging if the smart charging service could not satisfy the trip demand. The EVs which do not subscribe the battery swapping service can still swap their depleted battery during the trip. So once the electric vehicles enter the charging facilities, the flexibility of the aggregated smart charging EVs can be collected, and the actual charging load for the battery swapping station and the fast charging station can be also collected. The correlation among these charging facilities can be also acquired by the independent system operator. This figure shows the logical view of the proposed energy management system architecture. The left side of this figure is stage 1, which is stochastic economic dispatch. The right side of this figure is optimal power flow, which is a second stage. Both stages use look ahead DC optimal power flow, which employs model predictive control. This figure shows the theory of the model predictive control. So at time step T, the current plant state is sampled and a cost minimization control strategy is computed for a relatively short time horizon, K plus P. In the future, only the first step of the control strategy is implemented. Then the plant state is sampled again and the calculations are repeated starting from the new current state K plus 1. The reason that we use two stages is that we can make use of both macro data, which is system-wide load forecasting data, and the micro data, which is advanced metering infrastructure captured electric vehicle activities. The stage 1 use medium-term forecast data and sample-based stochastic model predictive control. The second stage use deterministic short-term forecast data and track horizon certainty equivalent MPC. Stage 1, in stage 1, the rolling horizon window is 24 hours, and the time step is 1 hour. In stage 2, the shrink horizon window is 2 to 6 hours, and the time step is 5 minutes. The stage 1 will send the state of controllable loads and storage units as boundary conditions to stage 2. The stage 2 will coordinate individual EV charging and follow the first step dispatch solution. The information and plan asymmetry between stage 1 and stage 2 are composited periodically. If we regard the stochastic economic dispatch in stage 1 as the outloop MPC controller, and the OPF in stage 2 as the inner loop MPC controller, and the plant is the power grids with massive integration of electric vehicles and DRs. Then it retains a generic double closed loop model predictive control scheme. While the application of the control method here is electric vehicle grid integration, it can be applied to a system when it needs to coordinate system and individual objectives and constraints. It needs to meet the following 3 criteria. An established communication system between the system and individual objectives. The aggregated individual parameters are predictable, and the system dynamics do not vary sharply within a short time interval. In this section, system identification and electric vehicle charging infrastructure planning is achieved. With the advanced control and energy management scheme, the independent system operator can manage electric vehicles at large scale and optimize the overall cost. But we could not predict the correlations among smart charging and other charging methods until we reach to that point. In other words, the system has some unknown parameters. So we propose a new predictive learning model predictive control learning. The double closed loop MPC is a generic model of the previous energy management system scheme. Deterministic MPC are used in both loops for the planning purpose. In the first simulation, we assume that smart charging does not have a correlation with other charging methods. So the addictive fast charging, super fast charging, and battery swapping loads are 0. The system will return how many smart charging EVs will use fast charging, super fast charging, and battery swapping services. Then we use the actual simulation data to replace the predicted value and run the double closed loop MPC again. This figure shows the implementation steps of the MPC learning method. We first run the double closed loop MPC, then the offline adaptation. It will stop until the system cost of the next step is close to the current system cost. So it can deploy, so the overall architecture deploys an indirect adaptive control scheme, and it can estimate the unknown dependency among different EV charging methods. Once we identify the temporal or electric vehicle loads, the EV numbers and average charging time can be obtained. Then the charging capacity of different charging facilities can be calculated. The smart charging station requires chargers to turn on and off. The electric vehicles are parked for several hours, so a certain capacity should be reserved to meet the peak demand. Here the reserve is 30% in this research. To the fast charging station and super fast charging station, we use infinite queue. The arrival rate of the customers is a percent distribution, and the service time is typically an exponential distribution. In practice, there will not be an infinite number of the chargers. So we use the CQE model with very small queuing delay to approximate the infinite queue. The delay is set to be 1%, which means that the probability that a customer is delayed in the queue during peak hours is 1%. Regarding to the battery swapping station, we use the MD infinite queue. The arrival rate is also a percent distribution, but the service time is constant. We use a MDC queuing model with small queuing delay to approximate the MD infinite queue. Some case studies are provided in this section to show the effectiveness of the proposed approach. We use the modified IEEE 118 bus test system for the case study. There are 19 online conventional generators. These are the total capacity of the DERs. These are the EV customers using different charging methods. So the EV battery capacity is said to be 70 kilowatt hour, and the customer behavior is imported from the National Household Transportation Service data in Texas. These are the power levels of the EV charging stations. The top figure shows the EV load impacts on the original load profile in the system. So the curve with the blue color is the original load. The curve with green color is the original load plus all the EV load. And the purple curve is the DR generation. We can see the total EV load features a renewable failure characteristic in most of the time. The bottom figure shows hourly average numbers of electric vehicles in different types of charging stations for 10,000 smart charging EVs in the sample. We also simulate different battery subscription ratio. Let us first look at the base case. with 50% of battery swapping service subscription ratio. The EVs use fast charging, super fast charging, and battery swapping will be much smaller than the EV numbers in smart charging. Then we can look at the case with 100% battery swapping subscription ratio. We can see it can be shown in the green line that no fast charging or super fast charging EVs in these charging stations. To the 0% of the battery swapping subscription ratio, which is shown in blue curve. We can still see a few EVs using battery swapping service. This is because there are a few electric vehicles that have a long driving distance. Even the super fast charging could not meet the trip demands. Note that we do not break the electric vehicle trips and take extra time to charge the electric vehicles using conductive charging. So to our best knowledge, this is the first time to indicate how the change of battery swapping service subscription ratio could affect fast charging, super fast charging, and smart charging loads. The top figure shows the comparison of the hourly average number of EVs with smart charging service under 50, 100, and 150 DER power generation for 10,000 EVs in the sample. So compared with the base case with 100% DER power, the case with 150 DER power requires more EVs to match the VRE power output, especially during the seventh state, with an increasing DER power output. This figure shows a comparison of the original load and the net load profiles under 50, 100, and 150 DER power generation in the system. We can see with more DER power generation, 150 DER power in the power curve, the net load is further reduced. We define the rep factor as a minimum load over maximum load. We do not use load factor here since we need to pay more attention to the decrease of the net load when there is an increase in DER penetration. This table shows system performance indices under different DER and EV integration scenarios. The base case features 90% of the EV penetration and 100% DER power output. So the DER power is accounted for 35% of the total power generation, and the rep factor is 0.47. If we keep the same EV penetration and increase the DER power, we can see there's a decrease of the rep factor. If we keep the same DER power output, we can see the increase of the EV penetration will improve the rep factor. When the DER generates more than 50% of the power, the rep factor is very small, even with 90% of the EV penetration. So the system will require higher rep rate generators and more storage units to maintain the system stability. The first table shows the coordinated expansion of the EV charging infrastructure, and the DERs are needed to trade off less impact to grid stability and more DER generation supply for clean energy transition. And the system planner can have a roadmap to coordinate the EV charging infrastructure and DER expansion using this table. The second table shows the capacity provisioning results for 10,000 smart charging EVs in the base case scenario. And also how many charging facilities are needed, as shown here. Also, for example, it can be seen that smart charging stations for 10,000 EV customers will need 2,091 smart chargers. So with this method, it enables the backward planning of the EV charging infrastructure, since the coordinated planning considers different electric vehicle and renewable penetration levels, and avoid a situation where the charging stations are built based on current charging demands and will need costly facility upgrades later. The proposed model can also study impacts of different EV customer behaviors and regions. This is a California case. So we reverse the wind and solar power output. Again, the purple curve is the DER generation, and the original load plus all the EV load is represented by the green color. We can see the EV load still shows renewable solar characteristics than most of the time, but we see there will be more EV charging load than the daytime to match the high solar power output. And we also import the EV customer behaviors from California state. So we know that the California network net load has changed from the dark curve to canyon curve in 2023 because of increasing solar power output. The large-scale smart charging EVs will mitigate the canyon curve in California. In order to achieve that, it needs fast deployment of EV charging infrastructure in California. But before we build this EV charging infrastructure, we should first build the advanced metering infrastructure and DER communication networks. The first table shows the computation results of MPC learning under different EV samples in the base case. We can see the model can simulate different EV numbers, and the simulation time will only increase a little bit. This is because we employ multi-agent system to monitor and control the EVs. The model can also simulate spatial temporal EV charging load if the location of the EVs can be acquired. as this is a sample-based method. But how to get large-scale spatial and temporal EV charging data will be a major concern for using this method. The second table shows the capacity provisioning results in the California case. So compared with the base case in Texas, the number of smart charging and fast charging and super fast charging facilities increases. The demand for battery swapping loads is reduced. This is because the average driving distance in California is less than that in Texas. And more EV charging load can be satisfied by the smart charging, even this customer subscribe to the battery swapping ratio services. We highlight the contribution of the work in last session. In summary, our research helped to optimize the strategic transmission planning to achieve a smooth clean energy transition. The proposed method can quantify the correlation among different EV charging loads, so that the system planner will have better understanding of the equilibrium of EV charging load ratio with respect to the charging changes in the EV charging methods. It can also simulate impacts of different EV and DER penetration levels to the grid. So the system planner can trade off DER, energy supply expectation, and power grid stability concerns. Besides, we calculate the charging capacities of different charging stations. The decision makers will know the equilibrium of adequate charging facility and less investment. The proposed method can strategically guide out the integration of electric vehicles and renewables to achieve the clean energy transition goals. This is because we make use of the proposed model predictive control learning. So MPC learning employs double closed loop MPC and adaptive control. So it relies on explicit models and can provide performance guarantees. It also allows for accurate representation of individual constraints, and it can estimate unknown system parameters. So the MPC learning can be used in many engineering domains which have explicit models. Compared to the MPC learning, machine learning is a black box where neural networks are used. It may face some difficulties at incorporating complex physical constraints, and it also needs output to train the model. So it is suitable for complex systems which cannot be described by a mathematical model, or the optimization problem itself is hard to solve. Both MPC learning and machine learning have their advantages and disadvantages. They can be used in different situations depending on the problem we need to solve. This presentation is mainly related to our two publications which are open access online. These are the previous works that's related to the presentation. Some of the previous research projects are supported in part by NERIC and DOE. Some of the previous work was also done at Smart Grid Laboratory of George Washington University. The work I present here is not relevant to the work I'm doing at Amazon Web Service currently. These are the 5 references we used in the presentation. Thank you. Any questions?
Please post in chat box. Raise your hand.
Sorry, Mandu, I could not hear you.
Dear participants, if you have any questions, please post in the chat box.
Oh, okay. Let me go back and see. Oh, okay. No questions?
Yeah, there is a question. How can EV charge with this innovative system? How can EV charge with this innovative system?
Oh, I see. How can EV charge with in this innovative system? Okay. So yeah, this is a good question. If we see the previous slides, let me go to here. Actually, we have 2 charging methods. One is using the advanced metering infrastructure to turn on and turn off the EVs. And the system is going to allocate the power without violating the EV charging constraints. This is suitable for the households in a community. And another method is a DR configuration for the smart charging station. So we can either turn on and off the EV charging constraints and also the duty cycle of the electric vehicles. So in general, uh, these are managed by the communication. These signals are communicated by the this system, and the system is going to calculate the charging a priority for the electric vehicles.
Okay. There is one more question in the chat box. On what system you have to implemented this new technique apart from modified IEEE 118 test system?
Uh, Sorry, I kind of have difficulty to hear what you are saying. Uh, could you type here in the chat?
Yes. On what test system, on what test systems you have implemented this new technique apart from IEEE 118 test system?
Uh, Sorry, I still hear some breaking voice over you. So
Type to the chat box. On what system you have implemented this new technique apart from 118 modified?
hold on a second. Let me maybe change my. Sorry, Mandu, can you type into the chat box?
Yeah, I already posted.
Okay. Okay.
On what system you have implemented this new technique?
Oh, so I see. What test system you have implemented this new technology? Uh, we so we just run it in the simulation. We can see here is a 180 bus system, and we don't use actual system to do the test, but we can see what we can see here is that our communication signals can be communicated through the existing communication network. But we don't have actual system to test our algorithm.
Uh, there is no questions from the chat box.
Okay.
Can you wind up the session?
Yeah, thank you, Mandu, for hosting
Thank
this
you.
webinar.
Thank you, Dr. Bowen, for readily accepting our invitation. And thank you very much for IEEE PS YP Chair, Mr. Alvin Powell, and my technical activities coordination team. Thank you very much, one and all. This is the time to uh, submit your feedback link. I'm sharing the feedback link in the Google in the chat box.
Okay, thank you, guys.
Thank you, Wong. Thank you, Dr. Wong. Thank you.
Thank you. Bye.
Yeah, thank you. Participants, please fill the feedback form. It's posted in the chat box.
Sorry. Yeah, we can stop now. Yeah.
Yeah, yeah.